Welcome to lecture 13 of our course on high performance computing. As you will recall, in the previous two lectures we have started looking at the software side of the system as far as what is required for the execution of our programs. And towards the end of the previous lecture we had looked into the very important piece of software known as the operating system. So let me just start off with a brief recap from the previous slide, where we saw that the operating system is the critical software on a computer system. It manages the resources of a computer system. And so from the perspective of what happens to your program when it executes, the software system is clearly very important. The software system is managing the hardware and software resources. We had seen that we need to understand four aspects of what the operating system does: how it manages the CPU, the sharing of the capabilities of the CPU among the different programs in execution, how it manages the main memory, ensuring that one program cannot access and modify the variables of another program, for example, how it manages the I/O devices such as terminals, monitors, disks, network interface cards, etc. We will not be looking at all of these examples, but one. And finally, how it manages the software resources of a computer system. And the key concept here was that when a program is in execution, we have the concept of a process, and the operating system manages the different processes which are sharing the resources of a computer system. So our first look into operating systems is in the area of how the operating system manages main memory. And we are looking at a specific kind of widely used operating system mechanism for managing main memory. This is known as paged virtual memory. And I just remind you that it is necessary to have a mechanism to protect one program in execution from another. That is typically done through a procedure of address translation. In other words, a program in execution will address its text, data, stack, and heap using maybe addresses between 0 and some maximum address based on the size of an address. But these addresses would not really be main memory addresses. They would be referred to as virtual addresses. Each process would have its own virtual addresses, and these would ultimately be translated when the programs execute into actual main memory addresses, which are called physical addresses. So to do this translation, a table of the mappings between virtual addresses and physical addresses is necessary. And we understood in the previous lecture that unless we do this carefully, the size of the table, the size of the address translation table, could itself become a major problem. We saw, for example, that if we were to associate a piece of address translation information with each byte address, so if the virtual address that in the diagram here we have an example of an address translation table. In this example, for each virtual byte address, it has the corresponding physical or main memory byte address. And the size of this table can be calculated. For example, if I assume that the size of an address is 32 bits, then I note that the width of the table, in other words, the size of each physical address, could be 32 bits. And I know that the number of entries in the table is going to be the number of bytes that can be addressed, and that's going to be 2 to the power 32. And therefore, the size of the table would be an enormous 16 gigabytes. So the address translation table itself, the information which is needed to translate a virtual address to a physical address, would be much larger than most main memories. So this is clearly not possible. We therefore looked at what would happen if you did not maintain a piece of address translation information for each byte address, but rather, let us say, for each 256 byte unit of memory. In other words, for the whole first 256 bytes of memory, in other words, from the byte address 0 to the byte address 255, I might just have one address translation information inside the address translation table. And if we do this, then the size of the table comes down to a more manageable 64 megabytes. So this is generally the kind of idea we are going to look at in the case of paged virtual memory. So since the size of the address translation table is the problem, it looks like a possible solution is by not maintaining the address translations on a byte by byte basis, but rather at some larger granularity, such as the 256 byte granularity which I had suggested. Now, technically, the word page is used for this size of granularity. So it is a fixed size unit of memory for which a single piece of address translation is maintained. as I said, in the example I had just gone through, I was assuming that the size of each page is 256 bytes. And as a consequence, 256 contiguous or neighboring memory locations will all be associated with the same piece of address translation information. And in effect, we are breaking the memory down into units of size 256 in order to solve the problem of huge address translation table size. So you'll recall that I talked about paged virtual memory. We now understand where the first term is coming from. We already know that we're talking about virtual memory because the addresses which a process uses are not real addresses but artificial or virtual addresses. Hence the name of paged virtual memory for this mechanism for setting things up, using fixed size chunks of memory, contiguous, as the unit for address translation. Okay, now let's get some idea about how this works. I'm going to do this to start off with just a pictorial representation. So we know that when a program is in execution, we refer to it as a process until it does a fork, after which it could be more than one process. But as far as a single process is concerned, we know that it has many things in memory which must be present in memory for it to execute. This includes, as we know, its text, which is its instructions, its static data, its stack allocated data, and its dynamically allocated data in the heap. So all of this put together is what we refer to as the virtual address space of the process or the program in execution. So until now, when we talked about programs, we were looking at the virtual address space in this way. We also know that this virtual address space can be viewed as the addresses from 0 up to some maximum possible address. So in this notation, rather than writing address 0 at the top and address 2 power 32 minus 1 at the bottom, I'm showing you the addresses in hex notation. Remember, whenever you see a number which is prefixed by 0x, that means that it is being shown to you in hexadecimal or hex notation. Hex is a short form for hexadecimal or base 16 notation. So the address space here, you'll notice there are 8 zeros in hex, which means that this is a 32-bit virtual address. So the minimum possible, the first 32-bit address is all zeros, and the last 32-bit address is all Fs. And if I had expanded this into binary, it would have been all ones, which is the value 2 power 32 minus 1. All right, so this is the way that I would use the virtual address space in terms of its address space. Now, if I'm going to try to manage the address translation information in units of 256 bytes, then the first 256 bytes would be at the top of the address space, going from byte address 0 up to byte address 255. The second chunk of virtual address space of size 256 bytes would follow, and so on. In fact, the actual addresses associated with each of these chunks could be calculated. For example, I know that in the first chunk of size 256 bytes, I know that the first address is 0, which means that the last address is going to be 255, because all the bytes between 0 and 255 would constitute 256 bytes of memory. And if I convert 255 into binary and then into hexadecimal, I will find out that it is FF, 6 zeros followed by FF. Similarly, the second 256 byte chunk in memory will start from 100, which is the address after 0FF. The address in hex after 0FF is the address 100. And the second chunk would run from 100 up to 1FF, and so on. So I could, given this 256 byte granularity assumption, I actually can redraw the picture of the virtual address space along these lines. Chunks of size 256 with clear knowledge of what the first address in the chunk is and what the last address in the chunk is. Now I'm going to be using the word page to refer to these chunks. So technically I could talk about that first chunk of size 256 bytes, which runs from address 0 up to address 255, or in hex, from address 00 up to address FF, based on the information which I see in this diagram to the left. You notice that I've highlighted among the addresses of the bytes which are in that first chunk, I've highlighted what they have in common. And you notice that what they have in common is that in all of those bytes, all of those byte addresses, the first 6 hex digits are all zeros. And in fact, if I look at the second chunk of size 256 in the virtual address space, I notice that for it too there's this commonality. All of its bytes, what they have in common is that their first 6 hex digits are 0, 1, or 1. If I was to convert that 0, 0, 0, 0, 0, 1 into decimal, I would refer to it as 1. Similarly, the 0000000, I would refer to as 0. So what the first 256 bytes have in common is that their most significant bits amount to 0, and what the second chunk of 256 bytes have in common is that their most significant bytes have in common is the 1. And therefore, in short, what I could do is to refer to the first 256 bytes in memory, since I'm going to refer to them as a page, and I know that this is the virtual address space, I can refer to those first 256 bytes as the virtual page 0. In other words, the virtual page in which all of the bytes have 0 as their common most significant bits. Similarly, the virtual page 1 as the virtual page in which all of the bytes have in common their most significant address bits being 1, and so on. Another way to look at it is, if I numbered the virtual pages from the first one in memory onwards, the first one would be called virtual page 0, the second one would be called virtual page 1. But this is an additional observation of some value, that within virtual page 0, all the bytes have their most significant bits identical as far as the address is concerned. And the commonality is that those most significant bits amount to 0, which is that virtual page number. In short, we have this picture. Rather than thinking of the virtual address space of a process as text, data, stack, and heap, we can abstract out what is being stored at which part of the virtual address space and view the virtual address space as this sequence of virtual pages, starting with virtual page 0 and going all the way up to, in this case, virtual page hex FF, whatever that may be. We need not convert it into decimal, but we'll just leave it in that form. Okay, now let's look at this a little bit more critically. This is how we are going to chunk the different bytes in memory for the purpose of address translation. But let's consider one of these bytes in particular. The byte which I have highlighted happens to be in virtual page 2 of the address space of the process that we're looking at. I'm sorry, it happens to be in virtual page 1, which is why the most significant bits of the address amount to 1. They are 0000001. And if I look at the least significant bits, they contain the byte address 24. So if I was to think about it carefully, within that virtual page 1, the first byte would have had the least significant 2 bits 00. The second byte would have had 1, and so on. So in some sense, I know that this particular byte that I'm referring to by address here is somewhere within the page. It's not the first byte, it's not the last byte, somewhere in between. And in fact, this 24 tells me exactly where it is located within the page. Right? It is the byte just after the byte number 23, which is the byte just after byte number 2, and so on. So I know its exact location within the page. So by the page number, I know which page this byte is associated with, and the page number is given to me by the most significant bits of the address of the byte. And within the page, I know exactly which particular byte is being referred to by looking at the least significant bits of the address. Okay, so that's the general idea of how these addresses are going to be viewed. Now, how is paged virtual memory going to manage an address space? Here we have this picture of how it's going to view the virtual address space. But ultimately, the objective is to translate virtual addresses into main memory addresses. So into this picture, we must include a picture which includes what main memory looks like. So let me add that over here. So as far as main memory is concerned, what do we expect to see? We know that the address translation information is going to be managed in a table, and within that table there's going to be one entry for each virtual page, which means that there will not be a separate entry for each byte, but only one entry for each virtual page, which means that any one of these virtual pages can map into one unit in main memory, and the address of that unit in main memory is what will be contained within the address translation table. Therefore, it follows immediately that main memory too must be viewed as being just a sequence of pages, and that's what we will refer to as the physical address space. So the physical address space is the range of main memory addresses which actually exist, hence the name physical. It's a real thing as opposed to virtual, which is artificial or imaginary. And for this particular example, I'm going to assume that the size of the physical address space is such that the first address in hex is all zeros, and the last address in hex is FF. So you'll notice that this is 6 hex digits, which means that this is a 24-bit address, which means that in actuality I'm able to address, unlike the virtual address space, which was a 32-bit address and which could therefore refer to 4 gigabytes of information, the physical address space is significantly smaller. That's the assumption which is being made in this diagram. And in fact, the size of the physical address space is only, if you do the calculation, 16 megabytes. But if that's all the memory that I have, then physical memory, the main memory that I have, then this would be the size of the physical address space. All the addresses from 0 up to what is the range of addresses that are possible in the amount of main memory that I have. So this is clearly not an unreasonable example, since you do know that there may be some machines in which there is only 16 megabytes of memory. As a consequence, the address space on that machine in terms of physical addresses would be only from hex 0 up to hex FF. Okay, so from our discussion from a few seconds back, we understand that the physical address space must be viewed as being a sequence of 256 byte chunks, because there's going to be a mapping between a chunk here and a chunk from the virtual address space and a chunk on the physical address space. So we therefore view main memory 2 in this way. There's the first chunk of 256 bytes which runs from address 0 up to address FF, physical address FF, and then there's the second chunk, and so on. And just as we call the first chunk in the virtual address space virtual page 0, we'll refer to the first chunk in the physical address space as physical page 0. And once again, if I looked at the most significant bits of the addresses of all the bytes in that first page, I would find out that they had the value 0, which is the virtual physical page number. So just like the virtual address space is a sequence of virtual pages, the physical address space is a sequence of physical pages numbered from 0 on upwards. And at any given point in time, the way things are managed by the virtual memory system is that a page in virtual memory will be mapped into a page in physical memory. So let's suppose, for example, that virtual page 1, which is the page we are currently concentrating on, is mapped to physical page 0, which is the page that we have in this diagram over here. What does this mean? It means that the operating system, or inside the address translation table, there is a mapping information which tells me that all the bytes which are associated with virtual page 0 are actually present in this range of the main memory. That's what the address translation table will tell me. And more specifically, if I was concerned about that yellow byte, the byte with address virtual address 00000124, then its position in main memory would be at the same displacement from the beginning of the page as far as virtual page 1 was concerned, the same displacement from the beginning of physical page 0. And that information is entirely available to me by the number 24, hex 24. Therefore, the address translation table tells me where in main memory this particular page is going to be, the fact that virtual page 1 is mapped to physical page 0, and that 24, in other words the byte address within that virtual page, tells me specifically which byte in main memory this virtual address corresponds to. And that's the complete picture as far as address translation is concerned. This is basically what the hardware has to do whenever there's a load or store instruction in order to translate the address from a virtual address into an actual main memory or physical address. Note that the addresses that we're talking about to the right are the actual addresses of the memory chips inside the computer, the thing which we call the main memory. These are the physically occurring memory cells within the computer. Okay, so what then is involved in address translation? So the purpose of address translation is to translate a virtual address as generated by the processor into a physical address. And you'll remember that the processor generates a virtual address whenever there's in the case of the MIPS1 instruction set, whenever there's a load instruction or a store instruction, or don't forget, whenever an instruction itself has to be fetched from memory. So for any kind of data access out of memory, or for the fetching of an instruction from memory. In all these situations, the processor generates a virtual address. This virtual address must be translated before it can be interpreted or sent to memory for accessing the data or the instruction. So we now look at the virtual address as the most significant bytes and those least significant bytes. For example, in the case of the particular byte that we were interested in, we looked at the most significant bits of the address, which were 00001, and the less significant, which were that 24. Okay. So the virtual page number, which was 1 for our particular example, I'm showing in this red hashed region, and the remaining bits of the address I'm showing in the unhashed region. Okay, so what has to be done in address translation? We understood that as far as address translation is concerned, the net effect is going to be that the 2,4 is going to survive as the information about where within the physical page the particular byte that is being accessed is located. All that's going to change during address translation is that the most significant bits of the address are going to get changed from, in our particular example, from 1 to physical page 0. And that's what the address translation information would have contained. So the terminology that we'll use is, we now understand that when I look at a virtual address, I can look specifically at the least significant bits, which are just the offset within the virtual page, and the most significant bits of the address, which are what we will now call the virtual page number, such as virtual page 1 or virtual page 0 or virtual page 1, all the way up to possibly virtual page, in this case, Fs. And similarly, the most significant bits of the physical address are what we will now call the physical page number. I will abbreviate virtual page number as VPN and physical page number as PPN. And in passing again, just note that the least significant bits of the address will not be affected by address translation. The 2,4, hex 2,4 in our example was, even after translation, was still hex 2,4, since it is only information about where within the page the information that is being accessed is located. In essence, the address translation table contains this mapping from virtual page numbers to physical page numbers. This is what it might look like. The virtual page number is the pink bits, most significant bits of the virtual address. The physical page number are those green bits, the most significant bits of the translated or physical main memory address. So this is what we expect you might see if you looked into an address translation table. Now we can do a little bit better than this, in the sense that you'll notice that the virtual page numbers, the possible virtual page numbers vary from 0 all the way to the maximum possible virtual page number, all Fs. If I was to structure the table along the lines of what is shown in this diagram, then in order to look into this table for a particular virtual address, I would have to search through the whole table, unless I maintain the table in order of virtual address, virtual page number 0 at the top, virtual page number 1 after that, virtual page number 2 after that, and so on. In other words, if I structure the table so that the first piece of translation information in the table is the translation information for virtual page 0 or virtual page number 0, and the second piece of translation information is the translation information for virtual page 1, and so on, then instead of having to search through the whole table, I can just index into the table using the virtual page number of interest to me. And if I was to structure the translation table in this way, then there would actually be no need to store the virtual page numbers at all. All that I would have to store would be the physical page numbers. I would then index into the page table, or the address translation table, which contains all the physical page numbers, using the virtual page number of interest to me. For example, since I'm currently interested in translating virtual page number 1, I would not look at the first entry in the address translation table, but I would look at the second entry, which corresponds to virtual page 1. So along these lines, if I reorganize the table would look like this. So the table contains only physical page numbers, and the way that you look into the table is using the virtual page number, which is what I'm indicating over here. So in order to translate this particular virtual address, I use the most significant bits of the virtual address, which are what we call the virtual page number, to index into the address translation table. And what I find there is the translation information, which is the actual physical page number corresponding to this particular virtual page. From henceforth, instead of talking of this translation table, referring to this translation table as an address translation table, since we have organized it in terms of these pages, I will refer to it as a page table. This is a standard terminology. So the page table is a data structure or a translation table of this kind, which contains one piece of address translation information for each page, for each virtual page of the address space under translation. And I could therefore talk about any one of these entries in the page table as being a page table entry. So this happens to be the page table entry for virtual page number 1. Okay. So as we progress with our discussion of how page virtual memory is going to work, we will be adding more and more information into the page table entry. So in order to keep track of this, I will every now and then augment this particular slide. So just remember, at this point in time, what we expect is that the page table will contain one entry for each virtual page, and that the information contained in that virtual page, in that page table entry, is the physical page number for the page in question, right? PPN. At this point, that's all that seems to be necessary. But let's go ahead. Now, at this point, we've got an idea that in order to manage the size of the page table, it makes sense to maintain one page table entry for each page rather than for each byte. If we had maintained one entry for each byte, then we would not have called it a page table, but an address translation table of bytes. So, but in actuality, this doesn't really tell us how many processes are going to be able to share memory, share the same main memory. So we need to get a better understanding of what's happening. Once again, I'll introduce the general idea pictorially before we start looking at details. All right, so at this point, we know that there is main memory. Main memory is a real thing. There are also the different virtual address spaces of the different processes, but at this point I won't draw them since they do not really exist. In this diagram, I'm not going to draw things which do not actually exist on the computer system. We're just going to draw things which physically exist. So one thing which certainly does exist physically is main memory. Now, one thing which does not exist is the virtual address space, or the contents of the virtual address spaces of all the processes that could be running on the computer system. Now in this particular diagram, I'm assuming that there are some n processes. There could be 10 processes, in which case the last one would be P of 10. I'm numbering the processes from P1 through Pn. Each of these processes has its text, data, stack, heap, divided over a large number of pages, hundreds, maybe thousands of pages. And the terminology that we're using is that these are for example, these are the virtual pages of process 1. These are the virtual pages of process n, and so on. Now the contents of these virtual pages do not actually exist, because they're much, I mean, as we saw, before they can be present in main memory, they have to be translated. And it's conceivable that the size of main memory is much smaller than the sum of the sizes of all these virtual address spaces. Therefore, that's why the word virtual or imaginary is important here. These are things which cannot really exist in main memory for practical reasons. But then the question arises, where can the contents of these virtual pages be stored? It's not enough to just say that they cannot be stored in main memory because there isn't enough space. But if I do require, let's say, 100 programs in execution to be supported, let's suppose that n is equal to 100, then I can't just say, yes, you can have up to 100 programs in execution. I must make it possible for the contents of the virtual pages of all those 100 programs in execution to be remembered. They have to be remembered somewhere in the computer system. They can't just be, one can't just say that they're fictitious, they don't exist. There must be some place for them to be stored, which raises the question of where can they be stored. Clearly they cannot be stored in main memory. If you do a quick calculation, if I have 100 processes and each of them has 4 gigabytes of virtual pages, then that comes to 400 gigabytes of virtual address space. The sum total of all these virtual address spaces might be equal to 400 gigabytes. And I might only have 4 gigabytes of main memory. So the main memory is not the answer to this question of where will the contents of these virtual address spaces pages be stored. So we have to look back at the other kinds of memory that are present in a computer system. And you'll recall that when we talked about memory for the first time, I said we used the term memory to refer to anything that can be used to remember things. And we're currently in a situation where we have to find some form of memory which can store a large amount of information, 400 gigabytes of information contained in all the address spaces of all those 100 programs in execution. And very clearly memory, main memory, is not the answer to that question. We have to be looking at something which has much larger capacities, such as potentially a hard disk drive. Now we can rule out the possibility of VCD, DVD, since very clearly we will need some kind of memory which can be modified, and VCDs, DVDs are not that easy to modify. you do have rewritable DVDs, rewritable VCDs, but they cannot really be rewritten a large number of times and may not be that useful in this scenario. Magnetic tapes are not that widely available on computer systems today, which leaves us with only the option of using the hard disk drive to store the virtual address spaces of all the programs in execution. And therefore that's what I'll do. I'll assume that in drawing this diagram, which is telling us what's happening behind the scenes when addresses get translated, I must include a hard disk drive. So I'll do that. So in a sense, I'm going to include the hard disk drive. I'm showing the hard disk drive by this cylinder. That's just as a notation. So this is a hard disk drive, and the contents of the virtual pages of all the programs in execution, all the processes, for the moment, I'm going to assume are stored in the hard disk. So they are being remembered. That was our requirement. Okay, so a large number of these pages are occupying the hard disk drive. And as I said, for 100 processes, this could be as much as 400 gigabytes of information which is being stored on the hard disk drive. Now, at any given point in time, only some of those pages can be present inside the main memory. We've seen that the main memory is much smaller. Main memory may only be of size 4 gigabytes. And therefore, very clearly, all those 400 gigabytes of pages cannot be stored in the main memory. So some subset of those virtual pages of all the processes which are in memory will be actually available in the main memory of the computer system. Just note, I'm not talking about virtual address spaces anymore. I'm talking about the hard disk, which is a real part of the computer system. I'm talking about the main memory, which is a real part of the computer system. Okay, so the fact of the matter is, as I said, some subset of these virtual pages which are available in terms of their content on the hard disk, so some subset of them will be present in the main memory. Let's suppose for the moment that for simplicity, in this diagram I'm showing you a virtual, each of these processes has a virtual address space made up of only 4 pages. This is a gross simplification, but it will make the diagram a little bit easier. So there are only 4 pages in process P1, each of the processes, and in a similar simplification, I'm assuming that there are only 4 physical pages in main memory. Right? And once we understand this example, which has only 4 pages in each virtual address space and only 4 pages in the physical address space, it will be easy to extend the understanding to more realistic scenarios. So the current assumption that I'm making is, since main memory has space to remember only 4 pages, given the size of main memory, only 4 out of all these virtual pages can be present in main memory at a given point in time. And in the current situation, it looks like the first page of process P1 is present in main memory, along with 2 of the pages of process Pn and 1 of the pages of process P2. So those are the 4 selected pages which are currently present in the main memory. All the other pages are not present in main memory right now, but are safely available on the disk. What then will the address translation tables or the page tables for each of the processes look like? We can actually construct the address translation table for process P0 quite readily. Now, the address translation table for process P0, I'm referring to it as process P1, will have to contain one piece of address translation information for each of its 4 pages. If I refer to its 4 pages as 0, 1, 2, and 3, and here I'm trying to figure out what the address translation table or the page table of process P1 will look like. So, what is the address translation information associated with its page 0? I know that its page 0, the one which is at the beginning of its address space, is currently present in physical page 0. Therefore, if I looked at the page table, I would find that 0 maps to 0. What about the second page of page 1? In other words, the page whose virtual page number is 1. Remember, the virtual pages of this process are virtual page 0, virtual page 1, virtual page 2, and virtual page 3. It has only 4 virtual pages. Virtual page 0 is currently mapped into physical page 0. Virtual page 1, as we can see from the left-hand side, is not present, and therefore that would have to be indicated in the page table entry. There is no mapping for virtual page 1. Similarly, there's no mapping for virtual page 2, and there's no mapping for virtual page 3. So this is in fact what the page table of process 1 would look like. Similarly, I can work out what the page tables of process 2 and process n would look like. So just to confirm, as far as process 2 is concerned, its virtual page 0 is not present in main memory, its virtual page 1 is not present in main memory, its virtual page 2 is present in main memory in the third physical page. Hence, when I look at the page table entry of process 2, I find out that virtual page 0 not present, virtual page 1 no mapping, virtual page 2 is present in physical page 3. There is a mapping from virtual page 2 to physical page 3. And similarly, the page table entries for all of the processes within the computer system. So this is the collection of all the page tables for this particular example. I'm not showing you the remaining processes, but they would have similar entries. As you could imagine, if there are 100 processes, given the size of main memory, the page table entries for all the other processes would have no meaningful mappings. They would just have dashes for all their entries. Alright, so this is the address translation information. And this also tells us that this big step that we took, where we said that the contents of all the virtual pages of all the processes will be present on hard disk, gives us a clear indication that we will have to keep track of the addresses on the hard disk of each of the virtual pages of each of the processes, which means that if I go back to my picture of what a page, the information that a page table entry must contain, I will clearly have to add to that. Look at it this way: if there is a virtual page which is currently mapped to a physical page, then there will actually be an entry inside its physical page number. But if there is a virtual page which is not mapped to a physical page, then that means that it's not present in main memory, but clearly one must keep track of where it is present on the disk, for which reason we'll add one more entry into the page table entry, into each of the page table entries, and that is basically the disk address of that particular virtual page. Just note, we have been assuming that copies of all the virtual pages are present on the disk. Since there are going to be thousands or millions of such virtual pages present on the disk, we will have to know the address of each of them in order to read it out of the disk as and when it is needed. Which is why I add an entry, a field into each page table entry, which I will refer to as the disk address. And for the moment we don't know what a disk address would look like. We just assume that it is some information using which that particular page can be read out of the disk. And we'll learn more about disks later. But for the moment you could assume that the disk address is 30 or 40 bits of information using which the page can be identified, located on the disk. Right, so that's how we end up with this picture over here. And the situation as we have it right now is clear for 4 pages. If the virtual address space of each process is of size 4 pages, what if it's much bigger? Then there's going to be a lot more information stored on the disk. The size of each page table entry is going to be larger, and hopefully the size of main memory will be larger than what we have over here, this simple example of 4 pages. Okay, now this raises an interesting question. So the question is this: what if the system is in this particular state and process P1 now accesses a variable that is present on its virtual page 3. Now what is virtual page 3 of process P1? Remember, virtual page 0 is present in main memory, virtual page 1 is not, virtual page 2 is not, and virtual page 3 also is not. So again, just to make sure we understand what's being said, the question is, what if process P1 is in execution and it accesses a variable that is in its virtual page 3? What could be present in its virtual page 3? Remember that this is the virtual address space of a process. So it's possible that if the heap of the process is growing from bottom upwards, that it could be a dynamically allocated variable that we are referring to over here. So one of the variables of the process is accessed by the program in execution. A load word instruction is executed on that address. That's the scenario that is being raised over here. Now the problem, as you can see it, is that that particular page, virtual page of process P1 is not present in main memory and therefore cannot be accessed using a load instruction. because the load instruction can only be used to actually access something which is in main memory. If it is not in main memory, then clearly it is not it is not accessible unless some more work is done behind the scenes. Now this situation that has just been described, one where a process tries to access a variable and it is identified that that particular page is not present in main memory, this situation is what is referred to as a page fault. Right? So this is a technical term. This is the situation where a virtual address generated by the processor is translated, or an attempt is made to translate it, and it is found that this particular virtual entity is not currently present in the main memory. So the question is, what can be done? Clearly we cannot say, oh, the bad luck of the program will have to stop. Very clearly the program must be allowed to continue execution. All of these features about address translation were added so that many programs could correctly execute sharing the resources of a computer system. A page fault is hopefully just a minor stumbling block towards the programs being able to continue execution. But clearly also the page fault must be rectified. Something must be done to remedy the situation, as a result of which the piece of data which the program is looking to access should become available in main memory. Right? Now the page fault would have been detected when an attempt was made to translate the address, and as you will notice from the previous slide, in this particular example, when process P1's address of something on page 3, when an attempt was made to translate the address, it would have been noticed that there is no mapping, which is a clear indication that there is a page fault. The page required, the virtual page required, the page fault, is what we will refer to as the page fault handler shortly. Now what must the page fault handler do? Okay, now in order for the processor's request for that particular piece of information to be satisfied, the page containing that piece of information must be brought into the main memory from its location on the disk. In order for it to be brought into the main memory, one particular slot or one particular physical page in the main memory must be identified for use by the page that is now going to be brought in from the disk. So that's the first step as far as handling the page fault is concerned. You must identify a slot or a physical page number to be used in main memory for this particular page. After this, the page could conceivably be read from the disk. Remember that each virtual page is present in disk as a copy. So a disk read can be used to read the contents of that page from disk into the slot or the physical page in main memory. After this, the page table entry can be updated. It can be updated in setting its valid bit to 1 and putting the correct identity of the page, physical page number, into its PPN field. So that's all that we mean by updating the page table entry. So this is essentially what would have to be done by the operating system's page fault handler. So the page fault handler is going to be a small piece of code inside the operating system to handle this possible scenario, the scenario of the page fault. Okay, so once this has been done, the load word instruction can be successfully executed by the processor. So the processor which had executed or tried to execute the load word instruction, as a result of which an address translation was attempted, as a result of which the page fault was identified, which initiated the execution of the page fault handler, can now return back and complete the execution of that load word instruction. That's what it boils down to. Okay, now there is one problem which arises in this context, and that is, it may not be as easy as you would think to identify a slot in main memory to be used in order to bring in a copy of the virtual page required by the process in question. And let's see why. Okay, now from the suggestion that a slot in main memory is to be identified, the immediate suggestion is that the operating system must keep track of the available unused physical pages. If it keeps track of which pages in main memory are currently not used, then identifying the slot in main memory is quite easy. It will just take one of those pages from among all the physical pages which are currently not being used for any virtual page. You can just pick one, and it could maintain the operating system might maintain all this information in a singly linked list, for example, which might be called a free list. Therefore, if the situation is that the list contains information about free physical pages, then step 1 of the page fault handler is quite easy. Just take the entry from the front of the free list and use that particular page as the slot in main memory where the virtual page can be read from disk. But what if the free list is empty? As in the example that we had in our diagram, all of the 4 physical pages in main memory are currently being used, and therefore the free list of unused pages in physical memory would be empty. What if the free list is empty? Once again, this cannot be used as an excuse to terminate execution of the program which caused the page fault. This too must be correctly handled. This must be covered by the page fault handler. This is just another contingency that has to be taken into account. So what should be done if the free list is empty? In other words, what if all the main memory physical pages are already mapped to virtual pages, as in our 4-page example? Then what the page fault handler will have to do is to actually make space within the main memory by evicting one of the currently used main memory pages or physical pages. Right? So the page fault handler must then identify a page to be replaced or evicted from main memory. Once one of the currently used pages in main memory is evicted or eliminated, then the required page which caused the page fault can be read from disk into that particular location in the main memory. So this is an additional functionality that would have to be taken up by the page fault handler. The task of identifying a page for replacement or eviction from main memory. And what I mean by eviction or replacement is actually removing that page from main memory in order to create an empty page in main memory which can be used for some other purpose. In this particular example, the other purpose is providing space for an as yet unused page which is available only on disk to be stored in main memory so that the process which accessed a variable on that page can successfully continue execution. So we have reached a point where we need to understand on what principles an operating system page fault handler could decide which page it can replace from main memory in order to make space for another virtual page. And as you can see, we are coming to a point in our discussion of main memory which may be of interest to us as far as people who write programs are concerned, because with this understanding we realize that there's a possibility that when our program is in execution, it may suffer a situation where some of the pages which it is using in main memory may actually get replaced in favor of the pages of some other process. And if this is the case, then we do need to know a little bit more about how the decision about which page to replace is made by the operating system's page fault handler. So this is a somewhat important consideration which will have some impact on the efficiency with which our programs execute. And since this is such an important breakpoint, we'll stop here for today. When we continue in our lecture number 14, we will try to understand the kinds of considerations which are used in the operating system page fault handler in order to decide which page can be replaced from memory. So from among all the pages which are currently present in the physical memory, which one can be replaced or evicted, thrown out of physical memory to make space for another page which is currently required. Thank you.